Right, here we go. So today we're going to learn the work and energy theorems. This is a lot in one video, and I've tried to break this up into smaller bits, and I think it causes more problems than it solves. So here we go. We're going to just do this, all right? So we're going to learn about the work and energy theorems, all right? So far we've learned about different types of energy, right? Kinetic energy, elastic potential energy, gravitational potential energy, and we've learned how to calculate work, all right? So we've learned that if your force is constant, then you can calculate the work done by a force by multiplying the force by the displacement. And this is assuming your force is parallel to your displacement. And if not, then we, do a little bit of trig, right? Where you split your force or your displacement up into components, all right? Another thing that is worth reiterating is remember that if we're trying to calculate the work that Roy does, then that's dependent on the force Roy exerts. All right, if we're trying to calculate, the work that gravity does, that's going to depend on the force of gravity. So they kind of get paired up a little bit, right? Now, if the force is not constant, then we calculate work by taking the integral of the force with respect to position, okay? And notice this is usually going to be a definite integral. So you're going to integrate from some initial position to some final position, right? And again, same idea. If you're trying to calculate the work that Roy does, you're going to integrate Roy's force, etc. Okay? And then finally, we learned the graphical version of this, that if you have a force versus position graph, that you can calculate your area, and that gives you the work, right? All right, and then flipping this all around, we can go backwards, right? So we could calculate, if we knew the work, we could calculate the force, right? So the force is the derivative of work with respect to position. Or if you're given a work versus position graph, then the slope is the force. Okay, so this is stuff we've learned, all right? But what we really haven't done is talked at all about what this work is. How does the work affect the energy of your object? All right. So let's take a minute. Let's consider an old kinematics equation. All right. So here's an equation we learned even in honors physics. 2a delta x equals vf squared minus vi squared. All right. So let's move the 2. All right. I'm going to divide both sides by 1/2. Or, well, divide both sides by 2, all right? So we get acceleration times displacement equals 1/2 vf squared minus 1/2 vi squared, all right? And now what I'm going to do is I'm going to multiply both sides by mass. So I get mass times acceleration times displacement equals 1/2 mvf squared minus 1/2 mvi squared. Oh, well, this is net force times displacement equals KE final minus KE initial. Ho-ho, look what we just did. We just discovered the work kinetic energy theorem. Which says that, so notice, this side of the equation is simply my net work, right? Now notice here, I'm assuming that my net force is constant, all right? And your net force could be changing, in which case you'd have to do an integral. But essentially what we've just discovered here is that the net work done on an object is equal to the change in kinetic energy. This is of colossal and major importance. All right? And so because of that, we should probably take a minute and talk about what we mean when we say net work. Well, the net work is exactly that. It's the sum of all of our works. So it's the work done by Roy, plus the work done by gravity, plus the work done by friction, plus the work done by springs, etc. Okay? And so notice now we can combine this with what we just learned, right? How do we calculate net work? Well, you can do net work is net force times displacement. If your net force is constant, you can do net work is the integral of your net force with respect to position, from some starting position to some ending position. If your net force is not constant, you can integrate your net force versus position graph and look at the area, okay? So this is important thing number 1. Okay? So that deserves arrows and rainbows and unicorns and all kinds of stuff. That is the work kinetic energy theorem. All right? So what else do we need to know? Well, when we did chapter 8, we talked briefly about the work done by conservative forces. All right? So remember, all right, so let's talk about the work done by conservative forces. So remember, a conservative force is essentially it's any force that has a form of potential energy associated with it, right? So what are our conservative forces? So for us, really, there's only 2. Gravity is a conservative force, and springs are conservative forces, right? There's a technical definition for conservative forces that I guess I should take a brief moment and discuss, right? So what makes a force conservative, right? Like, why don't we just make friction a conservative force and just create a form of energy called frictional potential energy? And the reason is a force only counts as, or a force can only be classified if the work done by the force, a force is only conservative if the work done by the force between 2 points does not depend on the path it followed. Okay? So the idea is if I pick a box up, from the floor and move it to here, then the amount of work that gravity does is the same regardless of the path that the box follows. Whereas if I push a box along a warehouse floor, the farther I push it, the more distance friction has to do work on it. Okay? So I wouldn't get too bogged down with that. I think essentially, as long as you remember that gravity and springs are the only conservative forces that we're going to deal with, then I think you're in good shape. All right? So what's true about the work of conservative forces? Well, it turns out that, the work done by conservative forces is equal to the opposite of the change in potential energy. All right? Think about that. If I lift a box, then I'm increasing the gravitational potential energy, right? So my change in potential energy is positive. But as I lift it, my displacement is up, my force of gravity is down, so the work done by gravity is going to be negative. And in fact, the equations are almost the same, right? So if I calculate the work of gravity, that's the force of gravity times the displacement. That's mg times my change in height. Right? Oh, but my force of gravity is negative. Oh, and that's the opposite of my change in gravitational potential energy, right? Okay? Same essential idea is true for springs, that when you squish a spring, the spring is working against you, right? Let me just do this. All right, so if you imagine squishing a spring, all right, as I squish the spring, I'm increasing my elastic potential energy, but as I do that, my displacement is this way, the force of the spring is this way, so the work of the spring is going to be a negative number, right? And so it turns out the amount of work that the spring does is equal to the opposite of the change in elastic potential energy. Okay? So that is our second kind of big idea, is that the work of a conservative force is equal to the opposite of the change in potential energy. Once again, stars, unicorns, rainbows, all kinds of stuff. This is super important. All right? So let's combine those 2 facts. All right, so check it out. So here is what we have just learned. We have learned that if we calculate our net work, that's the change in kinetic energy. And we've learned that if you calculate the work done by conservative forces, that is equal to the opposite of change in potential energy. Sorry about the hesitation there. So, what about the work of non-conservative forces? Well, it turns out that the work of non-conservative forces, and remember, non-conservative forces is essentially any force other than gravity or spring, that gives us our change in total energy. Okay? We used this all the time in honors physics. All right? So here's what I'm going to do. Let's take this, whoop, and I'm going to move it down here. And let's take this, whoop, and move it up here. All right? And what we're going to do is we're going to go, boom, add. So look, our net work, what is that? That's the total of all possible works, right? Well, every force is either conservative or non-conservative. So if I take the work done by my non-conservative forces plus the work of my conservative forces, that's going to give me my net work, right? That's going to give me my total work. Similarly, if I take my change in total energy and subtract my change in potential energy, that's going to leave me with my change in kinetic energy. Okay? All right, so these three lines written here on this screen, let me clean them up so that's all that's left on the board. These three rules are sections 9.1 to 9.3. Okay? I cannot understate the importance of these. All right? Very, very important. All right? So we talked about network, so I guess let's do our quick refresher here. So to calculate our network, that's our total work, right? So like I said, it's the work of Roy, work of gravity, work of friction, work of springs, etc. Similarly, our work of non-conservative forces would be exactly that, all of our non-conservative forces. Let's see, so that's Roy. Gravity doesn't count because it's conservative. Oh, friction would be non-conservative, and spring is conservative, right? And then the work of conservative forces would be the work of gravity plus the work of springs, all right? So these equations combined with our different methods for calculating work, right? I guess we might as well put everything on one page, right? So work is force times displacement for a constant force. Work is the integral of force with respect to position for a non-constant force, and then you've got your graphs, right? Force, position, work, right? So this slide right here essentially has everything you need for sections 9.1 to 9.3. So let's see if we can apply this and actually, use it and do some calculations, all right? So let's see. Let's go back to here. Now, do I want to talk about this? I guess we should talk about this really quick. This is a quick side note. Friction is a non-conservative force. So it turns out that if you calculate the work done by friction, it gives you the opposite of the change in heat. All right? So essentially, if a box is sliding across the floor, friction's going to work against it, right? So our work of friction is going to be negative, and in exchange, we're going to gain heat energy or thermal energy. So friction does 20 joules of work, or negative 20 joules of work. That means we gain 20 joules of heat energy. All right, I don't want to get bogged down on this because it's, at most maybe one multiple choice question on the AP exam, but worth commenting on, all right? As you lose energy because of friction, you gain heat energy, all right? And what I usually call total energy is, technically speaking, called mechanical energy, all right? Okay, so let's do an example. All right, so here we go. Whoop. Oops. All right, so let's consider this image here at the right. So what it tells us is the ramp is inclined at an angle of 30 degrees to the horizontal. The mass of A is 6 kilograms. The mass of B is 4 kilograms. The spring has a constant of 80 newtons per meter. We're going to hold it at rest with the spring in its relaxed position. The system is then released. We've got friction here between block B and the ramp. So let's make a note. Our force of friction is 12 newtons. And question A wants to know sort of how far is the system going to move? So let's think about what's going to happen. So gravity is pulling A down. And in exchange, it's going to pull B up, right? We're going to have two forces pulling B down, right? Force of gravity parallel is working against it. We're going to have the force of spring. We're going to also have force of friction. Holy moly. So we got a lot going on here, right? And so the idea is, as the system moves this way, this force of the spring is going to get bigger and bigger and bigger, and eventually the system will stop moving forwards, right? And so what we're going to do is we're going to calculate how far it moves before it stops moving. All right, so there are a number of ways we can do this. And I think there's some value in understanding both, the different methods. All right, so let's do this. Part A, how far will the block A move before the system stops moving? All right, so let me kind of clean up my drawing here. And let's suppose that block A moves a distance D, okay? That means in exchange, well, not in exchange, but in addition, block B will move a distance D. All right, we're going to be interested in the height. All right, so notice for block A, the distance it moves is the same as the change in its height, right? I guess technically, change in height for A is going to be negative, right? For block B, what's happening is it's going up an incline, right? And so since this angle here is 30 degrees, the change in height for block B is just D times the sine of 30, which ends up being just D over 2. Okay? All right, so let's use that and see if we can figure out what's going on here. All right, so how far will block A move before the system stops? So what I'm conscious of is the fact that we've got some a non-conservative force here. We've got friction. So that makes me think maybe I should do this. Maybe I should start with this fact. I know that the work done by non-conservative forces is simply my change in total energy. Okay? So for us, that means the work done by friction is equal to the change in gravitational potential energy for block A plus the change in gravitational potential energy for block B. Notice I have to separate these because the two blocks have both different masses and different changes in height. All right, we've also got a change in kinetic energy, which I don't need to separate because both masses are going to always have the same velocity. All right, and then as our spring stretches, we're going to have a change in elastic potential energy. All right, so let's think about what's going on here. So our work of friction, well, as the block moves up the ramp some distance d, friction is going to pull back with a force of 12 newtons. So it looks like the work done by friction is just going to be negative 12 newtons times d. Okay? The change in GPE for A, well, that's going to be the mass of A times 9.8 times the change in height, which is simply negative d. Okay? And then the change in GPE for block B, well, it's got a smaller mass, 9.8, and we decided the change in height for it is going to be this d over 2, right? Okay? All right. So, change in GPE for A, change in GPE for B, change in kinetic energy. Well, the block is going to both start and end at rest, right? We're trying to figure out how far it goes before it stops. So our change in KE is simply 0. And then finally, our change in EPE, well, as the system moves, our spring is going to stretch by a distance of d. So that's going to be 1/2 times our spring constant, which was 80. Oops. Try that again. Times the distance it got stretched squared. Okay? So, All right, so now we just got to solve this mess, right? So I'm looking at negative 12d equals negative 58.8d. Let's see, 4 times 9.8 divided by 2 is 19.6d plus 40d squared, and solve for d, right? I'm not going to grind through the algebra, but if you solve this, you get an answer of 0.68 meters. All right, so that's the distance the system moves before it stops. Okay? All right, so that's one of the ways of solving this. Now, let me point something out, because my students always say, like, how do you know where to start? Well, I mean, I guess the big thing is starting with thinking about how the energy is going to change, right? And so in this one, I established, oh, we've got this non-conservative force. Let's see how that affects the total energy, right? Another way you might solve this problem is to do this. You might go, well, it starts and ends at rest. So I know that my change in kinetic energy is 0. Oh, remember, the net work is equal to the change in kinetic energy, right? So let's try solving it that way. All right, so let's see, our net work. So that means the work done by gravity plus the work done by the spring plus the work done by friction all equals my change in kinetic energy, which is 0, right? So what's the work of gravity? Well, that's the opposite of the change in GPE plus the opposite of the change in EPE, right, for the springs, plus the work done by friction equals 0. And notice if I now add these to the other side to get rid of the negatives, then I get work of friction is change in GPE plus change in EPE, which is exactly the same as I got up here when I did it the first time, right? The work of friction is the change in GPE plus the change in EPE, and our change in KE didn't matter because it was 0. All right? So, there we go. All right, let's find the maximum velocity of the system now. How am I doing on time? Holy moly. All right, maximum velocity of the system. Whoop. All right, maximum velocity of the system. So this is a super common type of problem. All right, so our maximum velocity occurs when the derivative of velocity is 0, i.e. the acceleration is 0, which means our net force is 0. Okay, so let's think about what forces are acting on the system, all right? So, whoop. All right, so what do we got? We got the force of gravity. So what I'm doing right now is I'm looking at the two-object system, all right? And I want to find out when the net force on this is 0. All right, so the force of gravity on object A is going to be 58.8 newtons this way. We're going to have a parallel component of gravity on B, which we decided was 19.6 newtons, right? Just mg sine 30. We've got force of friction. Oh, man. Which was, what, negative 12 newtons? And then we've got the force of the spring trying to prevent it from stretching. So when these all cancel out, our net force will be 0, right? So let's see, we got 58.8 minus 19.6 minus 12 minus the force of the spring has to be 0. Algebra, algebra, algebra. Solve for the force of the spring, and you get 27.2 newtons. Oh, and that's equal to k times x, right? So now I'm just going to go 27.2 newtons equals 80 newtons per meter times x. Divide both sides by 80. And you get x equals, I believe it's yes, it is 0.34 meters. All right, so now what we're going to do is we're going to find the velocity when that occurs. All right, and so doing that is almost the exact same calculation we just did, but this time our change in kinetic energy isn't going to be 0, right? So what I want to do is I want to find so we know that the maximum velocity occurs when x is 0.34. So now I want to find the velocity at that point. So I'm going to use the change in total energy again. I think that's easier just because there are less negatives to deal with, kind of. All right, so let's try that. All right, so here we go. So the work done by non-conservative forces is our change in total energy. So the work of friction is our change in GPE for block A, plus our change in GPE for block B, plus our change in elastic potential energy, plus our change in kinetic energy. All right, so the work of friction. Okay, so what we decided was, I guess I should do this real quick. So we decided that our system was going to move through a distance of 0.34 meters, right? So now we can use that. So the work of friction, we're going to have negative 12 newtons times 0.34 meters. Change in GPE for A is going to be the mass of A times 9.8 times the distance it goes down, which is going to be negative 0.34 meters. Plus the change in GPE for B, which is going to be its mass times 9.8 times the distance it goes up. Remember, that's that whole 30, 60, 90 triangle thing, right? So if it travels 0.34 meters up the ramp, the distance it's going to go up is going to be half of that, so 0.17 meters. All right, let's see, plus our, oops, I wanted that to be orange, plus our change in EPE, which is going to be 1/2 times our spring constant of 80 times the distance the spring gets stretched, which is going to be 0.34 meters. Don't forget to square it. Plus, finally, our change in kinetic energy. Notice that's final kinetic energy minus initial kinetic energy, but because we're starting at rest, our initial is 0. So this is 1/2 mass. Well, how much mass is moving? Well, both blocks are moving, so that's a total of 10 kilograms moving at some velocity. All right, and so there's your equation. You just algebra, 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 solve for your V, and you end up getting 0.96 meters per second. All right, so there's a lot going on there. But notice, what it boils down to is essentially these three guys here, right? All right, let's try another one. Sometimes you'll be given a graph like this. So here it says, consider the graph below. It represents the vertical force Roy is applying to a 0.1 kilogram block as he moves it from rest up from the floor as a function of the vertical distance he's moved it. What's the velocity of the block when it is 7 meters up? So it looks like we've got this block that's sitting on the floor. We've got this upwards force of Roy, which is given from the graph, and we've also got gravity. It's a 0.1 kilogram block. So our force of gravity is going to be 0.1 times 9.8, so that's negative 0.98 newtons. All right, and so here, again, it's asking about the velocity of the block. And we've only got one non-conservative force here. So let's try to solve this one using our network. No, I guess it doesn't matter. We can do either network or work of non-conservative forces. The graph shows us Roy's force, so let's focus on the non-conservative forces, all right? So the work of non-conservative forces is our change in total energy, which for us is our change in kinetic energy plus our change in GPE. All right, so we're going to move it. So this is the work of Roy is our change in kinetic energy plus our change in GPE. All right, so the work of Roy. Well, this graph here shows us the force of Roy as a function of position. So remember, the integral of the force of Roy with respect to position gives us the work of Roy, which for us means the area of the graph, right? So let's find that area. So this area here, 3 times 2, that's going to be 6 joules. This area of this triangle is 1/2 base times height, so half of 3 times 3, that's 4.5 joules. Let's see, down here it looks like we've got -1/2 joule, and this is -1 joules. So it looks to me like the work of Roy is going to be 6 plus 4.5 minus 0.5 minus 1. All right, our change in kinetic energy. Well, we start at rest, so that's just 1/2 the mass times the velocity squared. And then our change in GPE, well, we've got a 1 kilogram block moving up 7 meters. So mass times 9.8 times my change in height. And then there you go. Just go through, do your math. I'm going to skip the algebra. But if you solve this, you get 6.54 meters per second after you do the algebra. All right. Now, what's another way I could have given this to you? So in this one, I gave you this graph, right? Let's suppose that instead, so let's pretend that graph isn't here. Let's just whoop, get rid of that. Oops, try again. Let's pretend that graph wasn't here. Suppose I had told you, suppose I'd given you the same setup, but instead of Roy's force being given by the graph, suppose I told you that the force of Roy was, oh shoot, I have it written down somewhere. Where did I put it? Too many papers. Let's go 0.3 x squared plus 10. Okay, so again, this is a force that depends on position, right? So we would solve it the exact same way, except this time to calculate the work of Roy, because our force isn't constant, we would have to integrate Roy's force with respect to position from the starting position to the ending position. So you'd take the integral from 0 to 7 of 0.3. Oh, I'm sorry. I wanted this to be 0.03. Here, I'll put it in red just so that it stands out. X squared plus 10 dx. So take your integral, right? So this is 0.01 x cubed plus 10x, evaluated at 0 and 3. And plug in your numbers. Oh, no, I'm sorry. Evaluated at 0 and 7. My bad. Evaluated at 0 and 7. So 7 cubed is 343 times 0.01. So that's going to give you 3.43 plus 70. So 73.43 joules is the work done by Roy. And so then you go, all right, net work is our change in GPE plus our change in KE. No, my bad. Work of non-conservative forces, right? Work of non-conservative forces is change in total energy. And Roy is our non-conservative work, right? So you're going to get 73.43 is our change in GPE, so that's 0.1 times 9.8 times the 7 meters we're lifting it, plus 1/2 mv squared, and solve it. All right? Okay, but this just kind of shows you how you can combine these equations with our different definitions of work, right? You know, whether you're taking an integral or finding the area under a graph or whatever. Okay? I think we got one last example here. Yeah, this guy. All right. So this one's the real deal. So here what we've got is a kinetic energy versus position graph. All right. So I guess a quick note here. So I've got a kinetic energy versus position graph. So let's consider the slope of a kinetic energy versus position graph. So the slope of a kinetic energy versus position graph would be the derivative of the kinetic energy with respect to position. This is the same as the derivative of our net work with respect to position, right? This is essentially the D is similar to it's like a calculus triangle, right? D just means a very small change. So this is saying if I take a very small change in kinetic energy with respect to position, well, change in kinetic energy is net work, right? So I'm looking at the change in the net work with respect to position, okay? And so this gives you the net force, right? Because we know that net work is the integral of net force with respect to position. So conversely, the derivative of net work with respect to position gives you net force. Okay, so this is a really common trick. Okay, so the derivative of a kinetic energy graph with respect to position is net force. All right, now this isn't a thing that I've memorized. What I do have memorized is change in kinetic energy is net work, and net work is the integral of net force with respect to position, right? And then I'm just kind of putting these ideas together, okay? This is, if you're keeping score, essentially a combination of this equation here, oh, yellow is a bad choice, and this equation here, right? Okay, so anyway, so let's get back to business over here. If you haven't taken a break, this might be a good idea. Just take a quick break here. I know this video is long. Keep in mind this one long video here is now replacing 3 old videos. And we'll just spend more time on this section to make sure you have time to practice it. All right, so we've got this kinetic energy graph. It represents the motion of a 6.25 kilogram block. So our mass is 0. Oh, no, it isn't. It's 6.25 kilograms. So what's happening is the block kind of begins at rest, and then we're going to squish the block to the left a distance of 4 meters and hold it at rest. And then we're going to let it go, and it's going to go springing back to the right, and it gets to all the way over to a position, it gets only to a position of 1 meter before it stops again. Okay, and the graph shows us the same thing, because notice our vertical axis here is kinetic energy. You can see that at a position of -4, our velocity and therefore kinetic energy are 0, and then it springs back to the right and gets back to a velocity and kinetic energy of 0 here at x equals 1. Okay? And so based on all of this, what we're going to try to do is figure out both the spring constant and the force of friction. All right? So because this is a kinetic energy versus position graph, we want to kind of focus on kinetic energy, right? So what do we know about kinetic energy? Well, we know that our net work is our change in kinetic energy. All right, and as the block slides back and forth, what forces act on it? Well, there's gravity and normal force, but those are perpendicular to the motion, so they don't do work. So all we're going to care about here is the work of friction and the work of the spring. So now, to consider change in kinetic energy, we need a starting point and an ending point, right? So notice I look at this and I see 4 points that seem important. So at this point, at x equals -4, I know my kinetic energy is 0. Up at this point, I know my kinetic energy is 12.5 joules, but I can't exactly tell what that position is. It looks like it might be about -2.5, but I'm not sure if it's exact, okay? Over here, I know that if the position is 0, the kinetic energy is 8 joules, and over here, I know if the position is 1, the kinetic energy is 0, all right? So let's focus on I don't know, one of those. Let's maybe start over here, because at this point, my change in kinetic energy is going to be 0, right? So let's start there. That feels like maybe it'll buy us something. All right, so let's see. So let's go from x equals -4 all the way over to x equals 1. So our net work, so that's going to be the work of the spring plus the work of friction is our change in kinetic energy, which is 0. So the work of the spring, that's equal to the opposite of the change in elastic potential energy, plus the work of, oh, did I say the work of Roy? It's embarrassing. It was supposed to be the work of friction, right? So the work of friction is, well, let's see what's going on here, right? Our block is going from a position of -4 to a position of 1. So our displacement's going to be 5 meters, and friction's going to push against it. That's an unknown. So we got force of friction. I guess let's tack a negative on there, right? Because we know that the force of friction is going to be negative. Times the distance it goes, which is 5 meters. That's got to be 0. All right, now what about the change in elastic potential energy? We actually want the opposite of the change in elastic potential energy, right? So the opposite of our change in elastic potential energy is the opposite of EPE final minus EPE initial. Well, distribute this negative here, whoop, whoop, and you end up getting EPE initial minus EPE final, which is 1/2 K times my initial position squared minus 1/2 K times my final position, squared. So I'm looking at, let's see, -4 squared is 16, so I'm looking at 8K minus 0.5K is 7.5K. That's my change in elastic potential energy. So here's my final equation. I'm looking at 7.5K minus force of friction times 5 meters equals 0. Let's get rid of that M there. It's just units, right? Better yet, let's do this. All right. Oh, shoot. I have 2 unknowns, right? So now what I want to do is choose another point on the graph and solve this again. All right. So what I'm going to do now is, let's this time, instead of going from -4 all the way to 1, let's go from -4 just to 0, because I know this point as well, right? All right, but it's essentially the same process. All right, so let's all right, so make a note of this because I'm going to erase it. All right. All right, so okay, so now let's see. So our net work is our change in kinetic energy. So once again, the work of the spring plus the work of friction is our change in kinetic energy. So the work of the spring, well, we decided that was EPE initial minus EPE final, right? Remember, it's backwards because of the negative sign. Plus the work of friction, which is our force of friction times the distance it's going to go, which if we're going from -4 to 0, that's just going to be 4 meters this time, equals our change in kinetic energy, which we're going from 0 up to 8, right? So our change in kinetic energy is 8. All right, so let's see, EP initial. So that's 1/2 K times 4 squared minus EPE final. Well, here our X is 0, right? So our EPE is 0. So I'm looking at 8K plus 4FF equals 8. And then we can combine that with the equation we had before, which was 7.5 K plus 5 force of friction equals 0. And now we've simply got a system of equations, right? So I'm not going to go through the algebra on this. You all hopefully by now know how to solve a system of equations. There's a couple of different ways of doing this one. But if you solve it, you end up getting that the force of friction is 6 newtons to the left, and your spring constant is 4 newtons per meter. All right. Oof. So there's a lot going on here. Again, if you only got one thing out of this gigundous video, this slide right here is where it's at. There it is. I'll leave that right there. Is there anything I'm missing? I guess let's scribble down those derivative equations real quick. Force is the derivative of work with respect to position. Again, you can combine this work with one of these changes in energy. And work versus position graph. The slope gives you the force. Again, if this is kinetic energy, then it would be net force. If this is potential energy, this would be the opposite of your conservative force. All right, so there we go.